Hello everyone, my name is Ivan Eryganov, and today I will tell you about application of quantum register algebra, and especially we will focus on construction of quantum circuits representing quantum games. My talk is a direct follow-up to the presentation of Professor Eryganov that he has given before the break. At first, I will introduce a game called Battle of Sexes and discuss its Nash equilibrium. Then we will proceed to the quantum domain, and I will demonstrate representation of quantum battle of sexes using the Q array. The presentation will be concluded with the demonstration of the computational possibilities of Q array using Gallup-Web and MATLAB. The classical battle of sexes is a game between two players where each of them choosing between two alternatives. In our example, players are deciding on which movie they are planning to watch. So we have two alternatives: comedy movie or drama movie. Each player has preferred type of movie, but if they fail to agree, they do not watch any movie at all. So as you can see, the payoffs for each combination of strategies can be represented using these two tables. And you can see that, for example, the player A prefers comedy, whereas player B prefers drama. So the main controversy of this game is that it has two pure Nash equilibria, and both of these equilibria are unfair. It has mixed equilibrium, which if we will play this game repeatedly, will lead us to the state then players are failed to agree in more than half of rounds of this game. I've been asking myself, is there a possibility to obtain different results using alternative approach? And recently, game theory has been enriched with a new class of games, and it is class of quantum games. So general quantum games can be characterized as games which include superposition of players' strategies and entanglement of their decisions. Originally, quantum game theory studied quantization of the non-cooperative matrix form games, such as well-known Prisoner's Dilemma. And it has been demonstrated that some non-trivial equilibria can occur then we enable the superposition of player strategies and fully entangle their decisions. So now I'll demonstrate how we can represent quantum computing in the quantum battle of sexes using the Q array. So you can see this scheme, this quantum circuit, which in fact represents the game. In order to represent the game, we associate the basis states of qubit 0 and 1 with the decisions of the player. So decisions comedy represented as cat C represents cat 0 and drama represents cat 1. So as you can see, each player starts with the basis state C, and we obtain the 2-qubit state CC cat, which can be represented in Q array as follows, as you can see. So in fact, it is simply the idempotent of 2-qubit system. The main thing, so you should understand that we are starting from the state that both players are agreed on comedy. So after we have our starting state, we entangle the states, and we use the following entanglement operator J hat, and it has parameter gamma. Their gamma has the following range, and the main thing that if we use the entanglement 0, gamma 0, so our entanglement gate simply degenerates to identity operator, and if we use p half, when it will create the Bell's state. So this gate, which we now have written down in direct notation, can be represented in Q array, as you can see over here. And the main thing that I also have simplified these associations between bra and cat notation. So you can see that the first expression indeed connects the bra and cat representations of the basis states, and it is connected using the idempotent, but then I just simplified these expressions. After we have performed the entanglement, players are able to apply their strategies. So their strategies are simply 1-qubit gates, and we apply the tensor product. So we apply the tensor product of 1-qubit gates. So it somehow can be interpreted as the independence of players' decisions. So each player can operate with his qubit or her qubit as he wishes. So you can see that we now representing it as a subset of special unitary group of the dimension 2, and this subset can be described using these two parameters. So after players have applied their strategies, we have to disentangle the resulting state before we perform the measurement. In order to perform the disentanglement operator, we have to use the conjugate and Q arrays. You can see here denoted by the dagger. And in fact, when we apply the conjugate, representation of all expressions in the brackets is still valid. And the only thing that should be performed is change of the sign of a complex unit. So you can see now that we have obtained our final state CF cat, which is in fact, we have to read it from the right to the left. So it is state CC on which we apply the J hat entanglement operator when we have applied the tensor product of the strategies operators, so the 1-qubit gates, and then we have disentangled the state. In order to obtain payoffs of players, we have to somehow express it using the expected payoff, so it is just the expected value of the payoff, and this expected value overtakes the values from the table. So you can see that, for example, for the player A, CC probability is multiplied by 10 and DD by 7, otherwise it will be 0. And for player B, these two values are interchanged. The most important thing that these probabilities are computed as follows. So you can see that we are simply perform the measurement, and the squares are squared like this bracket expression, and obtain the real analogy of the probability. So now I will demonstrate how to establish these pair of functions and work with them using the framework of Q-array implemented to the Gallup, and when we will proceed to the calculation of the Nash equilibrium of this game using MATLAB. So I have prepared the TXT file, so you can see better. I will just show it over here. So you can see what we have. The first thing we have to do when we work in the Q-array, we have to define this complex unit, analogy of complex unit, using two additional elements of the basis of the geometric algebra. and then using this complex unit, we can define the width basis. After we have defined the width basis, so now you can, for example, see that F1 and F1T means the F1 dagger. After that, I can define the idempotent, which simply looks like this. And we have to proceed to our starting state. Our starting state is cat00, or as you have seen, cat-cc, which is simply the idempotent, which is multiplied by 1. Then we have to define also bra vectors to measure our final state. And they are defined as follows. Again, it's completely corresponds to the association that have been demonstrated by Professor Eryganov in previous presentation. So now I simply have rewritten how looks the entanglement and disentanglement gate. The one thing that should be emphasized that now we are using this complex unit that have been constructed using the basis elements of the geometric algebra. So iota is over here. Sorry, and after that, and for moreover, we have changed the name of the gamma to entanglement. Yes. So after that, I just directly write down how looks the elements of the strategies. So if you have seen there was the matrix which represents the 1 qubit gate, and I just simply define these elements using 2 parameters for each player. So for the first player, it looks like this, and for the second player, it's still the same, but now it has other parameters. So phi1, theta1, phi2, theta2. So the only thing that is the most challenging in the computation with the Q array, but I think that is only a matter of time. It is the tensor products have been discussed before, because there have to be performed some sign changes when we're working with the tensor product. Because when we're working with the serial circuits, yes, we can't simply multiply these elements, but when we are working with the tensor product of the elements of the Q array, there can occur sign changes, then some specific monomials met during the operation. So due to this reason, I have introduced the artificial variable sign change, which you can find over here, and over here. So I will later, using the MATLAB symbolic toolbox, manually correct the signs. But for now, we are leaving it's just like this. And the final state, the CF, is just simple multiplication of all elements that we have computed before. And the last thing that we have to do, and output of our function, will be payoff of the player A and payoff of the player B. As you can see, I perform the measurement. Again, it's simply the corresponding bra vector times CF, final state of the game, which one is taken in absolute value and squared, and then multiplied by the corresponding value. The main thing that you have maybe noticed that I have chosen to represent it already as -1 times this whole expression. This is only technical reason that MATLAB has built-in solver for the non-convex optimization, non-linear optimization, which only minimizes. So in order to maximize this payoff, I have to take minus functions. So this is the reason why I'm using -1 over here. So if I just copy this whole expression and open the Gallup tab that currently runs on domain of our university, Brno University of Technology. I will choose the MATLAB output. Then I have to choose the quantum register GA, and I will maybe it will be better over here, and I then simply switch it to the 2 qubits in Q array and paste the whole expression. Now, for example, I will call it pair of functions, and I will run the compilation so I can obtain the result in Gallup, in MATLAB using Gallup. So yeah, you can see that now I currently obtain the MATLAB function that has the following variables. So entanglement, phi1, theta1 parameters of the first player, and phi2, theta2 parameters of the second player. And as an output, it has payoff of the player A and payoff of the player B. Yes, so you can see it. It is like really long expression, but for example, you can make sure that everything is computed correctly, because payoff A is only have only one element over here, as well as payoff B. It is simply the scalar. Yes. So now I just simply copy this function and paste it to the MATLAB. And the only thing that I have to do in order to work correctly with these expressions is to perform the sign change that we were talking about. In order to do this, I will slightly change the code. And in fact, I will use symbolic variables. So I just simply will make function which has no input, but has symbolic variables, and as well it will has the symbolic output. So, and now I find the last row, the tensor product is defined, and the only thing that I have to perform now is symbolic substitution. So I will simply write down subs, which is symbolic substitution for the function, for the same expression, and I will sign change variable squared to -1. The rest sign change simple will stay as 1. So I don't need to expand.
5 minutes left. 5 minutes.
Okay. So you can see that we have prepared our function. We can save it, and now this function will be used in this prepared script function, which computes the equilibrium. In fact, it will obtain this symbolic output and then convert it into MATLAB handle function, and by simple iteration of the optimization functions, it will try to find the fixed point of the best response of players, and if this expression will converge, we will find the Nash equilibrium of the game. So, for example, I will now simply write it over here, and gamma is now our parameter which corresponds to the entanglement, and if I will choose that we have 0 entanglement, but in fact there is no entanglement between players, we will obtain the original result of the game, that one of the player obtains 10 and the second player obtains 7, yes, and this specific values of the parameters. And for example, if I want to use the full entanglement, we will compute it as well. And you can't see that we have obtained this result. You can see moreover that values of parameters of the players haven't changed, but simple change in the entanglement between players have changed the payoffs, but in fact they are still in the same relationship, because before the first player obtained 10 and the second player obtained 7. In conclusion, I just would like to say that I think that I have convinced you that QRA is language that have provided us with a convenient tool to perform quantum computing, and in particular to study quantum games. And using the simple associations between direct notation and QRA, I was able to establish the whole game process and then convert it into MATLAB function, which then I have optimized in order to obtain the Nash equilibria of the game. Thank you for your attention, and now I will be glad to answer all of your questions.
Thank you, Ivan. Questions? So David asks, who won the game?
In fact, we haven't solved the game, and we have the same dilemma as it was at the beginning, because we have the two symmetric solutions, the two symmetric Nash equilibria as we have in the classical game. So in fact, we are still not knowing how to interpret this result.
Daniel asks, is it a fun game?
I don't think so.